Hi there, I'm Jeremy Krug and welcome to my 10-minute review of AP Chemistry Unit 9, covering Thermodynamics and Electrochemistry. If you learned something from this video, smash that like button and share this video with the other members of your AP Chem community. And don't forget that if you want even more review and practice, head over to ultimatereviewpacket.com and check out the full review videos along with hundreds of practice questions to get you ready for the big day in May. That's ultimatereviewpacket.com. Now, let's get started. We often describe entropy as the level of disorder in a system, or sometimes as how well dispersed the particles are. Since solids are very compact and not dispersed at all, they have the lowest entropy. Liquids have more entropy, aqueous solutions usually have even more entropy, and gases have the highest entropy. When you raise the temperature of a material, its molecules move faster, so that's more entropy as well. When you increase the volume for a gas, the molecules have more space to move around and disperse even more, so that's more entropy too. In this chemical reaction, we're going from all solid to a mix of solid and gas. So that's an increase in entropy. In a chemical reaction where every substance is a gas, the more molecules you have, the more entropy there is. So if you go from 3 molecules of a gas down to 2, that's a decrease in entropy. We can calculate the entropy of a reaction from the individual entropy values of the substances in the reaction. Take the sum of the entropies of the products and subtract the sum of the entropies of the reactants. This is basically identical to the process for calculating change in enthalpy that we did back in Unit 6. When a process tends to occur, we say it's thermodynamically favored. Gibbs free energy is a measure of the thermodynamic favorability of a chemical process, and it's abbreviated delta G. Delta G is negative for all thermodynamically favored processes. Delta G is positive when a process is not favored. Delta G, as well as delta S and delta H, are usually calculated at standard conditions, symbolized with this little degree sign. That degree sign tells us a process is at 25 degrees Celsius, 1 atmosphere pressure, and 1 mole per liter for any solutions. There are several ways to calculate delta G. One way is to take the total sum of the individual Gibbs free energies of the products and subtract the total sum of the Gibbs free energies of the reactants, just like we did previously for delta H and delta S. Another way is to use the equation delta G equals delta H minus the Kelvin temperature times delta S. If we know any 3 of these values, we can calculate the 4th. Just be careful with your units, because entropy is usually given in joules, and the others are usually given in kilojoules. The universe tends to favor exothermic reactions, which have negative values of delta H. The universe also tends to favor reactions where entropy is increasing, which has positive values for delta S. So if you encounter a reaction that meets both of those conditions, then it will be thermodynamically favored at all temperatures. On the other hand, if a reaction is both endothermic and decreasing in entropy, then it won't be favored at any temperature. If a reaction has a positive delta H and a positive delta S, then it will be favored only at very positive temperatures, high temperatures. Likewise, if a reaction has a negative delta H and a negative delta S, it will be thermodynamically favored only at lower temperatures. Sometimes you'll encounter a reaction that has an almost immeasurably slow rate, like the rusting of a car. The data may tell us it's thermodynamically favored, but it's so slow that we can't even measure its rate. This is called being under kinetic control. This usually happens when a reaction has a very high activation energy. It's not at equilibrium, it hasn't stopped, it's just very slow, if it even occurs at all. Kinetic control. Gibbs free energy is related to the equilibrium constant by the equation delta G equals negative R times the Kelvin temperature times the natural log of the equilibrium constant, where R equals 8.314 joules per mole per Kelvin. We're usually given the temperature, so if we know either the delta G or the equilibrium constant, we can calculate the other quite easily. This equation tells us that when a reaction is thermodynamically favored, its delta G is negative, and its equilibrium constant will be a very large number, so we'll have lots of product formed. Likewise, when a reaction is not favored, its equilibrium constant will be a very small number, as in much less than 1, so almost no products will form. Every ionic compound can potentially dissolve and dissociate in water. Take potassium chloride, which would dissociate by this equation. The value for delta G for this process is negative 5.3 kilojoules per mole. And that negative value tells us that it's thermodynamically favored. So KCl is soluble in water. But why? It comes down to the two driving forces, enthalpy and entropy. The enthalpy change for this process is positive, which is not favored by the universe. However, its entropy is increasing, positive, which is favored by the universe. In fact, the change in entropy is so favorable that it can counteract the endothermicity of the process and allow the process to occur. So examine the delta H and delta S of a dissolution process to predict if a compound will dissolve and under what conditions. Some reactions that are thermodynamically unfavorable can still happen. We might have to add external energy like electricity or even light. This is how you charge a cell phone battery or get carbon dioxide to react with water in photosynthesis. Another way is to couple the unfavorable reaction with a more favorable one. For example, obtaining copper metal from copper 2 sulfide by itself probably isn't going to happen because its delta G is positive, it's unfavorable. But if we throw in this equation that is favorable and then add them together, we see that we just need to react the copper 2 sulfide with oxygen in order to obtain copper from copper 2 sulfide, to have a process with a negative delta G. A galvanic cell is what most people call a battery. It's thermodynamically favored. It basically uses wires and electrodes to harness the electron flow of a redox reaction to power a load. We use a diagram like this to visualize what's going on in the galvanic cell. Each side of the cell has one specific half reaction that's taking place. The side where oxidation takes place is called the anode, and the side where reduction takes place is called the cathode. Red cat and NOx. Remember that the electrons flow through that wire from the anode to the cathode, like AC. If these are metallic electrodes, the cathode should always increase in mass. The cat gets fat. The salt bridge equalizes the charge as ions react at the electrodes. For the salt bridge, we use ions that won't react with anything else in the galvanic cell. So sodium and nitrate ions are common choices. At the edge of the salt bridge, cations flow toward the cathode and anions flow toward the anode. You can use the clues given to you in the question to figure out every one of these other details about the galvanic cell. Every galvanic cell has a cell potential, sometimes called its voltage or its potential difference. In our list of half reactions, notice that these are all written as reduction potentials, even though every redox reaction has one oxidation and one reduction. We use these standard reduction potentials as written and calculate our cell potential by taking the value for the cathode from the list and subtracting the value for the anode. The cell potential is related to the thermodynamic favorability of the cell by this equation. The delta G of the cell equals the opposite of the number of electrons transferred in the balanced equation times Faraday's constant, which is 96,485 coulombs per mole of electrons, times the cell potential. We can determine the N by balancing the equation. So if we know the delta G or the cell potential, we can calculate the other one. Cells with a positive voltage are thermodynamically favored, while cells with a negative voltage are unfavored and would need some external power source. We normally calculate cell potentials at standard conditions, which honestly aren't that common in the real world. For non-standard conditions, we use the Nernst equation. Some of these values don't change in a reaction, but we can change the temperature and concentration. If we increase the concentration of the products or decrease the reactants, that increases the reaction quotient Q, and that lowers the voltage. Conversely, decreasing the concentration of the products or increasing the reactants will decrease the value of Q, and that raises the voltage. Now, this is not Le Chatelier's principle because the cell is not at equilibrium. A galvanic cell at equilibrium is a dead battery and has a voltage of 0 volts. Electrolytic cells are non-favored processes which we have to drive using an external power source. These are often used for plating out metals. This equation is used for those types of processes. The current in amps equals the total quantity of charge transferred in coulombs divided by the time in seconds. So if we have this nickel plating process and we run a 10 amp current for 1 hour, which is 3,600 seconds, we'll transfer 36,000 coulombs of charge. To convert that into grams of nickel, we use stoichiometry. Step 1 is to convert to moles using Faraday's constant. The balanced half reaction tells us we need 2 electrons to produce 1 atom of nickel, and then we convert to grams using the atomic mass. That's Unit 9. Thanks for watching, and don't forget to like and subscribe, and check out my playlists for more AP Chemistry review resources. And don't forget to get the ultimate review packet for AP Chemistry to get the best review resources out there. In the next video, we'll be reviewing the laboratory techniques you'll need to know to ace the AP Chem exam. I'll see you then.